We're going to be looking at rates of change of linear and quadratic functions. Now, normally, this will be considered a set of data or coordinates, and we have actually two in our examples. But what I'm going to do is we're actually going to look at a different style, one that's very simple to recognize linear and quadratic. We're going to look at the algebraic form. So that's when it's written like an equation. In order to tell if something is quadratic or linear, we look at the exponent of the variables. And specifically, we look for the exponent of the highest variable. Okay? So in this case, we're looking at our x variable. Everything is set equal to y. When the exponent of the x is a value of 2, it is, anyone know? Quadratic or linear? Quadratic. All right. Quadratic, which means on a graph it makes some shape like that.
A U or a V.
For it to be linear, what must the exponent on the variable be? That's right. If there's nothing there, we assume the variable is 1. And if the variable is 1, that makes it linear, which means on a graph we have a straight line. Okay? Very simple to recognize. All you have to do is look at the equation. The two below are two that are not in what we call expanded form. These two here are technically in their expanded form. Okay? These are not. So in order to put them in expanded form, we have to distribute. Okay. Right. Once we distribute, it'll be a lot easier to tell if something is quadratic or linear. For instance, right now, the x is only to the power of 1. And in this one, both of the x's are only to the power of 1, which would lead us to believe it's linear. So, we'll distribute the 3, and that's going to leave us y equals 3x plus 6. What's the exponent to the x? Or sorry, yes, what's the exponent? So it means, what is this?
Linear.
It's linear. Great. In this case, when we distribute, what is x times x? That's right. And then minus 2x. What's the highest exponent? 2. What about this 1? Does it come into play?
No.
No, we focus on which one is the highest, which means this is what?
Quadratic.
This is quadratic. Okay, good. So you've gotten that part. That's roughly the easiest part. The other way to tell is if we have a set of points, which we started here. And what we're going to do with this set of points is we have to check two things. First of all, we check the independent variable. The independent variable is our x value. The dependent variable is our y. In order to check this, and we're going to be finding differences, we have to make sure the independent variable is going up or down by the same amount. What is the x values changing by every time? Yeah, it's going up by 2 every single time. And it's consistent. If there was an inconsistency, then we couldn't quite use this. Okay? It needs to be going up by the same amount. Now what we do is we do something called first differences, where we take the second value and subtract the first. Another way of looking at it is going from the bottom all the way up. Okay? You can do either method. So for the first one, we'll take the second value and subtract the first, which will give us 6 minus 3, which gives us what value? Good. Then we go 9 minus 6.
6 plus 3.
12 minus 9. 15 minus 12. 18. What are you guys noticing?
It's always 3.
Is it always 3? You've checked all of them?
Yeah.
Good. So, is it positive or negative 3?
Positive.
Positive. What this has told us, first of all, if the first differences are the same, that means we have a linear function. And the rate of change is positive 3. In other words, the slope of this is positive 3. That's what it's just told us from here. Okay? That's good to know.
How do we know it was linear again?
What's that?
How do we know it was linear?
Because the first differences were all the same.
Oh, okay.
So let's go down to the second example. Second example, this is our independent and our dependent. We need to check if the independent is changing by the same amount. Is it changing by the same amount every time? What's it changing by?
Positive 1.
Is it positive 1?
Yes.
Good. So it's going up by 1 every time. We know it's consistent, the independent variable. That's great. So we take first differences of the dependent. This time I'm going to start from the bottom and go up. It's the same idea. 25 subtract 16. What does that give us? 11? There you go. Okay. Then we take 16 and subtract 9. 9 subtract 4. 4 subtract 1. 1 subtract 0.
1.
0 subtract 1.
1.
Negative 1. 1 subtract 4. Negative 3. Now, are the first differences the same?
No.
No, so this is
Quadratic.
not linear. We know it's not linear. We don't know if it's quadratic. This just proves it's not linear. Okay? The second differences will tell us if it's quadratic. If they're the same. If the second difference is the same, all it tells us is it's not linear and it's not quadratic. It doesn't tell us what it is. Okay? These are just helping us to decipher if it's linear or quadratic. So second difference is we take the answers. Okay, and we'll do the same idea. We'll start from the bottom and go up. 9 subtract 7 gives us... Good. 7 subtract 5. Good. So you've noticed we're going up by 2 every single time, right? What do we got? 3 subtract 1 is 2. How about 1 subtract negative 1? Oh, I'm glad you know your math. And negative 1 subtract negative 3? Positive 2. Check it on a calculator if you don't got it. So, the second differences are the same. Therefore, this is a quadratic relationship. We've just discovered that by doing the second difference. Again, if they hadn't been the same, it just tells us it's not linear, and it is not quadratic in this case. These are the two things we looked at.